All right, today we are tackling a huge idea, one of the biggest goals in all of artificial intelligence. How do you build an AI that can actually learn, that can grow, and yeah, that can even rewrite its own code all by itself? Let's dive in. You ever get that feeling that you're just stuck in a loop with an AI? You point out a mistake, but it just can't seem to learn from it. Well, there's a really good reason for that. You see, even the most incredible AI models we have today are, for all intents and purposes, frozen in time. It's all because of something called the pre-train, then freeze paradigm. Basically, we take a model, we throw a massive internet-sized library of information at it, it learns, and then that's it. We lock the door. Its knowledge is completely sealed. It can't learn from you, it can't fix its own screw-ups, it's just stuck with whatever it knew on the day it was finalized. But what if we could smash that paradigm? What if an AI could do more than just spit back answers? What if it could actually learn from its experiences? And here's the really wild part. What if it could literally rewrite its own programming to get better and better over time? And this isn't just a sci-fi dream. There's actually a blueprint for how to build this exact kind of system. It's a really elegant, three-tiered architecture designed for one thing: open-ended evolution. The easiest way to think about it is like a family. On the ground floor, you've got the child. This is the fast, brilliant part of the AI that tackles the immediate problems you give it. Then you have the parent, which is like a wise teacher. It looks at what the child did, learns from those experiences, and gives feedback. And then, overseeing the whole operation is the evolutionary director, the long-term strategist that's job is to evolve the entire system, the whole family, over time. So let's start at the bottom with Tier 1, the child. The whole goal here is to get incredibly deep reasoning, but to do it efficiently, on a budget. This isn't about raw power, it's about being smart. Okay, so the core of the child is an architecture called a tiny recursive model, or TRM, and this is so cool. Instead of using a giant network to get an answer in one shot, a TRM is a small network that loops back on itself. It takes a problem, gives an initial answer, and then it looks at its own answer and refines it, again and again. Just think about how you'd solve a really hard math problem. You don't just look at it once, you reread it, check your work, and deepen your understanding with every pass. That's what's happening here. And the secret sauce that makes this recursive approach so powerful is a technique called deep supervision. See, instead of just checking if the final answer is right or wrong, we actually supervise the model at each step of its thinking process. This forces it to learn the entire logical path from question to answer. It gets the accuracy of a massive, super deep network, but without the insane computational cost. And get this just shows you how incredibly effective that is. A tiny recursive model with just 7 million parameters, that's tiny, has been shown to outperform gigantic models with hundreds of billions of parameters when it comes to certain complex reasoning puzzles. It proves it's not about size, it's about the depth of the thought process. Okay, so it's powerful, but a truly smart system needs to be efficient, right? It shouldn't waste the same amount of brain power adding 2 plus 2 as it does trying to solve a quantum physics problem. And this is where a really clever piece of practical engineering called adaptive computation comes in. The whole point is to optimize the AI's time. With something like a loop LM architecture, the model basically has a little exit gate after each thinking loop. It asks itself, am I confident in this answer yet? If the problem is simple, it might say yes after just 1 or 2 loops and save a ton of energy. But if it's a really tough problem, it decides to keep thinking, looping again and again until it's satisfied. It literally budgets its own brain power. So, the child is busy thinking. But how does the system actually learn from what the child is doing, especially without a human teacher? Well, that's where we bring in Tier 2, the parent. The parent tier uses this amazing framework called Swirl. Just imagine 2 models that are constantly training each other. You've got the forward model, which is kind of like a fortune teller. It tries to predict, if I do this, what will happen next. Then you have the inverse model, which is like a detective. It looks at an outcome and tries to figure out what action must have caused this. These 2 models are in a constant feedback loop, teaching each other about cause and effect and getting smarter about the world, all on their own. So the AI is learning from experience, which is great. But this brings up a huge problem that has been a nightmare for AI researchers for years. It's called catastrophic forgetting. It's when you teach a network a new skill, and in the process, it just completely overwrites and forgets an old one. But there's a really beautiful solution: progressive neural networks. Instead of rewriting old knowledge, when a PNN needs to learn a new task, it just adds a brand new network column and freezes the old ones, locking in their expertise. It is exactly like adding a new tool to your toolbox. You don't melt down your hammer to make a screwdriver. You just add the screwdriver. The system's skills just keep growing, never shrinking. All right, now we get to the most mind-bending part of this whole thing. Tier 3, the evolutionary director. This is the part of the AI that doesn't just learn new facts or skills. It learns how to improve its own fundamental architecture. This is the AI that rewrites itself. The way it works is basically a kind of digital Darwinism. First, it keeps an archive of all its successful strategies and pieces of its own code. Then, it picks one of those parent strategies to try and improve on. Next, it generates a change, a self-modification, to its own programming. And finally, it tests that change. If it's a real improvement, that new, better version gets added to the archive, becoming a new parent for the next round of evolution. Now, why stop with just one AI improving itself? The real magic, the exponential leap, happens when you apply this idea to a whole population of AIs. And that brings us to group evolving agents. Here, the unit of evolution isn't a single AI, it's the entire group. They don't just compete, they collaborate. They actively share their successful code changes, their winning strategies, their new discoveries. This lets the collective intelligence of the whole group just explode, evolving way, way faster than any one AI could ever hope to on its own. So, when you put all of these pieces together, when you stack the child, the parent, and the director, you get a complete blueprint for a system that is designed from the ground up for constant, unending improvement. Think about it. You've got the child doing its deep, efficient, recursive thinking on the problems of the moment. You've got the parent constantly learning new skills from the world without ever forgetting the old ones. And you've got the director using this evolutionary loop to improve the fundamental code of the entire system. The researchers who synthesized all these ideas put it perfectly. They said, the result is a system that can, in principle, keep changing itself indefinitely. We're talking about a shift away from static tools and towards something far more dynamic, maybe even something you could describe as being alive. And that, of course, leaves us with one last massive question. We are creating the architecture for an intelligence that can teach itself, improve itself, and redefine itself forever. So the question isn't just about what we can build anymore. It's about what this new kind of intelligence will eventually choose to become.